Hello viewers, welcome to this session on stereochemistry of carbon compounds. In our today's session, first we will review what we did in our last session about the stereochemistry. We will discuss today how to name these isomers. We call it as a configurational nomenclature. The nomenclature can be given as a relative configuration where two systems are being used. One is DL representation and 3O or erythro representation. And second, we will discuss absolute configuration where they are represented by letters R or S. Then we will discuss some terms which are generally used in stereochemistry, that is retention, inversion of configuration, racemization, and finally we will take up how these racemic mixtures can be separated, and then we will summarize our today's work. Now with the help of polarimeter, we can determine that which of these two isomers is dextrorotatory and which of these is levorotatory. But what arrangement of atoms represents a particular isomer, that we cannot know. So some nomenclature method was required for assigning the configuration. As we did in geometrical isomerism, these configurations were represented as cis or trans or by the letters E and Z, because when I say write cis isomer, you will be able to write the configuration for that particular isomer. So similarly, a system was required for naming the configuration in optical isomers. One of the method that was given earlier, that is a relative method, we call it as a relative configuration, and in this system glyceraldehyde was chosen as a standard for assigning the configuration. Glyceraldehyde, you know, two isomers are possible for it. These are the two isomers of glyceraldehyde. Now, what was being done, that any compound whose configuration is to be written, it was compared with glyceraldehyde. These are the Fischer projection representation for the two, and this is the asymmetric carbon atom of glyceraldehyde which has been shown in the box here. The substituent on this, the configuration around this carbon is compared with a particular carbon in any other compound, and that was assigned a particular configuration. When this system was given, even about glyceraldehyde, it was not known that which of these two configuration represents plus glyceraldehyde or minus glyceraldehyde. Arbitrarily, it was chosen that when in Fischer projection it is written and compound that has hydroxyl group on the right is called plus glyceraldehyde. Although later on, when methods were available, this thing was found to be true. The method was given like this, that any compound that can be obtained from glyceraldehyde or can be converted into glyceraldehyde by a series of reactions, those compounds are said to belong to D series, and the compounds which can be correlated with this minus glyceraldehyde, they are said to belong to L series, and we use letters capital D and capital L before their name. This system was mainly used for carbohydrates. It was given by Fischer at the time, who was working on carbohydrates, and carbohydrates are designated as D or L according to the stereochemistry of the highest numbered stereogenic carbon. Highest numbered stereogenic carbon means when a structure of a carbohydrate it is written in Fischer projection, we write the aldehydic group or carbonyl group towards the top side, and we compare the configuration of the lowermost asymmetric carbon atom. And on that carbon, if the hydroxyl group is pointing to the right, that carbohydrate is designated as D, and if it is on the left side, then it is designated as L. Let us see it with the help of example of glucose. This is the configuration of glucose, and in this glucose we start numbering 1, 2 from the aldehyde side, and this is number 5, that is the lowest asymmetric carbon atom, or highest numbered asymmetric carbon atom or stereogenic carbon atom, and it has hydroxyl group on the right side. So that is why this particular isomer of glucose is represented as D glucose. Similarly, its enantiomer, it has hydroxyl on the left side, it is represented as L-glucose. We can use this method for fructose also. In fructose, again we write the chain like this, and lowermost carbon in this isomer has hydroxyl on the right, then it is D-fructose. Method can be used for 5-carbon sugar also, like this is L-arabinose. Here the hydroxyl group on the lowermost asymmetric carbon atom, or the highest numbered asymmetric carbon atom, is on the left side. So that is why it is designated as L. So this method was used mainly in carbohydrate, then it was extended to amino acids also. In amino acids, they are also designated in the same manner. We only thing is look for amino group. If amino group is on the right side, then the isomer is designated as D, and if it is on the left side, it is designated as L. Such as this is alanine, where NH2 group is on the left side, so this is designated as L. But there are drawbacks of this method. The system is impossible to apply widely because we cannot compare a large number of molecules with glyceraldehyde only. Second, if you want to convert it, then we have to remember a sequence of reactions. Only then we can reach to glyceraldehyde, or we can convert from glyceraldehyde to that particular compound. And secondly, it is quite ambiguous method because many times the two enantiomers of the same compound can be correlated with the same isomer of glyceraldehyde. So this method could not be applied to large number of compounds, although in case of carbohydrates and amino acids this method is still used. Another method that was in use, that was derived from two sugars themselves. These sugars are threose and erythrose. Both are these 4-carbon sugars. In threose, the two hydroxyl groups are across when written in the Fischer projection, and in erythrose, two hydroxyl groups are on the same side when written in the Fischer projection. And these two sugars were used to compare the compound which have the substituents across, they are called threoisomers, and which have substituents on the same side, they are called erythroisomers. Like the isomers of 2,3-dibromopentane, the 4 possible isomers are these. These two isomers have the bromine atoms on the same side and enantiomer also, so they are classified as erythro, whereas when the two bromines are across, they are classified as threo. But again, this method arises some ambiguity. In what type of cases? The problem comes that which longest chain is to be selected for comparing the groups. Like in this compound, although R and R dash are different, but at least two X are same. So this is isomer which is called erythro, this isomer is called threo. But what to compare in this? If we write like this, we find that two hydrogens are on same side. If we write like this, we find that two hydrogens have become across each other, two methyls are also across each other. So whether this isomer should be written as threo or erythro. So this method was also not very useful for many compounds. Actually, what was required? An absolute method, a method which gives the configuration directly on the basis of the arrangement of atoms, and that system was R and S system. This R and S system is based on those CIP rules which we use for E and Z system for geometrical isomers. In this system, R and S are derived from two Latin words which are rectus and sinisters. Rectus means right and sinister means left, and these two words are initialized as R and S. We will just see what does it mean by right and left and how do we arrive at this configuration. But this system, as I said, is based on the actual arrangement of atoms, and if we say this compound has got, this isomer has got R configuration, R S configuration, we are able to write the configuration. And if the configuration is written in Fischer projection or in the form of the source projection or in any form, we can determine whether it is R or S. For assigning configuration by this method, there are two steps. Step 1 is that assign the priorities to the 4 groups attached to the chiral center according to the sequence rule. These sequence rules are the same which we have already discussed them while discussing EZ nomenclature for geometrical isomers. Here we sometimes use the term highest priority. Actually, if there are 4 groups, we will give them the priority 1, 2, 3 and 4. So, 1 priority means the group that gets the highest priority. Then second step is, now visualize the molecule in such a way so that the group of lowest priority means the group with the 4th priority, is directed away from the viewer, and observe the order of remaining groups. Means we view the molecule from such a direction that the group getting the least priority, 4th priority, is going away from us, and then we see the arrangement for remaining 3 groups with the priorities 1, 2 and 3. If in the sequence of 1, 2 and 3 our eyes travel in a clockwise direction, that is in the right hand side, we call this molecule to have R configuration. And if in going from 1, 2 and 3 we have to move anti-clockwise or counterclockwise, we assign it as a S configuration. Let us understand it with the help of this picture. Say this is a molecule where this is the group getting the 4th priority, this is the group with the 3rd priority, the 1st and 2nd priority. We have to view into the molecule so that the group of the 4th priority is going away from us. And now what is the sequence for 1, 2, 3? It is clockwise. So this is assigned R configuration. Look at this side. When we are viewing from the side, that group of the 4th priority is going away from us. Now our eyes have to move 1, 2, 3, that is in a counterclockwise. So such a arrangement will be given the S configuration. Let us understand it with the help of a model also. This is the representation of the model. Say these are 3 groups here. This is a hydrogen behind it getting the 4th priority. This hydroxyl gets 1st priority, CH2OH 3rd priority, this is an aldehyde 2nd priority. Now when we view from this direction, that is from your eyes, we have to move our eyes 1, 2 and 3, that is in a clockwise direction. So this is R configuration. Now let us understand this thing with the help of model. This is a model representing the same molecule that you have seen on the screen. This blue group 3rd priority, yellow group 2nd priority, red group 1st priority, and this is behind it the hydrogen getting the 4th priority. So now you have to view from this direction. This is the direction you have to view, and when you are viewing in this direction, in going from the group of 1st priority, that is red, to the 2nd priority, this is yellow, and 3rd priority blue, that is we are moving in a clockwise direction. So this molecule has got R configuration. So this is the way we can assign R or S configuration by looking at the model. But every time it may not be possible to make the model, and there may be some confusion when we have a tetrahedral structure written on our notebook or on board, etc. So what we can do, we can convert these into the Fisher projection and see that how we can assign configuration R or S using a Fisher projection for a molecule. In this case, if we write it in the Fisher projection, these are the 2 groups coming out of the plane. So they occupy this horizontal position. These are the 2 groups going behind. They occupy this position on the vertical line. And now next is that we assign priorities to these groups using the sequence rules. What we find that all these 3 groups are attached through carbon. So first atom is carbon. So priority cannot be decided on the basis of first atoms. This hydrogen obviously gets the 4th priority. Next atoms we see here, there are 3 hydrogens, there are 2 hydrogens, 1 oxygen, and there are 2 carbon and 1 hydrogen. So obviously here we get an atom of higher atomic number at the 2nd level. So this gets the 1st priority. Here are 2 carbons at the 2nd level, this gets the 2nd priority, methyl gets the 3rd priority, and hydrogen is assigned the 4th priority. So these are the priorities now. CH2OH group 1st priority, CH3 twice 2nd priority, methyl 3rd priority, and hydrogen 4th priority. Now, we have to view into this molecule from the direction so that group getting the fourth priority is going away from us. Now, as we know that in Fisher projection, the groups on the vertical line are going away from us. If we bring the group of the fourth priority to this position and then view the molecule from this side, from our side to this center, these three groups will be like this, that these two are coming out and this is going behind. So, they are just like as we are sitting on a driving seat of a car and these three groups are present on the steering wheel and this group is going towards the axle. So, just look at the steering wheel and see the position of these groups. But before looking at the sequence for the groups, we have to bring the group of the fourth priority to this position, and this we can do in Fisher projection by carrying out two interchanges. After one interchange of the groups in Fisher projection, we get the mirror image, and after two interchanges we get the same configuration. Now, we do a first exchange. Let us do this first exchange between this group number 1 and 4. We get this situation. Hydrogen with the fourth priority comes here, CH2 goes there. Then we can do any second interchange between these two groups or between these two groups. We will not use this hydrogen because we want to keep it here. So, after a second exchange, say between this methyl and CH2OH group, we get this situation: CH2OH, CH3 twice, CH3 and then hydrogen. Now, what we have to do? We have to look for the sequence of this 1, 2 and 3, and we find that sequence is clockwise. So, this isomer is assigned R configuration. Let us take another example. This is an isomer of glyceraldehyde where we have given the priorities. This hydroxyl group gets the first priority, CHO the second priority, CH2OH the third priority, hydrogen the fourth priority. Again, we do not have the group of fourth priority here, and we can bring it here by carrying out two interchanges. Let us say first interchange we do between this group 3 and 4, this comes here. Then we carry out a second interchange, say between this group and this group. The group with the first priority comes here, this is third priority, second priority. Again, now if we look at the sequence 1, 2, 3, we find that we have to move our eyes in a counterclockwise direction, and that gives it the S configuration. So, in this way we can assign R or S configuration to the molecules using Fisher projection. And also, if the molecule is given to us and we are asked to write the configuration, we can do in the same way, that we look for the 4 groups on the asymmetric carbon atom, give them the priorities, put a cross, put the group of fourth priority here, and then as per RRS we write the groups on these 3 lines. Now, we can have molecules with more than one asymmetric carbon atoms. If we have more than one asymmetric carbon atom, then this R or S configuration is assigned to each asymmetric carbon atom. Say this is an isomer we have plus tartaric acid. We want to assign the configuration at this asymmetric carbon atom. The groups attached to this carbon are carboxyl, hydrogen, hydroxyl, and remaining fourth group is actually this remaining part of the molecule. It is attached through carbon. So, the first atom at this first level we will consider as carbon. Now, let us assign the priorities. This hydroxyl group is attached through oxygen, gets the first priority. Hydrogen obviously gets the fourth priority. This is carbon, this is carbon, but here we find it is C double bond O and single bond O. So, all oxygens, where here this carbon is attached to one oxygen, one carbon and one hydrogen. So, obviously carboxyl group gets higher priority. So, this is second priority, this is third priority. Now, we can write on a separate cross these groups with these 4 priorities, carry out the interchanges, bring the group of fourth priority here and see the sequence. We will find that it is anti-clockwise and this is assigned an S configuration. Similarly, we can use this method for this particular asymmetric carbon atom using these groups hydrogen, hydroxyl, carboxyl and the remaining part of the molecule, and we again get S configuration. Similarly, we can assign configuration to all other isomers of tartaric acid. This one gets R and R configuration, this is R and S, this is S and R. Let us compare something that we have studied earlier. We find that this is an enantiomer of this, and in this enantiomer, if these asymmetric carbonates have got the S configuration, obviously mirror image will require R configuration. In meso, one carbon is R and other carbon we have discussed earlier is the mirror image of it. So, obviously we are getting S configuration for this. We get the mirror image of whole molecule, this becomes S, this is R. This actually represents the same molecule and it is optically inactive. This is what we have already discussed. So, this is about the nomenclature for configurations. Now, next we take up, there are certain terms which are used in stereochemistry. Generally, one of them is retention of configuration. Retention means something is retained. Now, what is retained here? It is configuration that is retained. Means if in a reaction a group is replaced by another group and group occupies the same position that was earlier occupied by the leaving group in the reactant, we say that it is retention of configuration. We can see it with the help of this structure. Say this L represents a leaving group, some reaction is carried out, but this group that has come occupies the same position and the position for all other three groups, it remains the same. Then we say that in such a reaction configuration has been retained. Another is inversion of configuration. Now, inversion of configuration is that if a net change of a reaction is substitution of a group on chiral center in the reactant in such a way that the incoming group occupies the position which is opposite to that which was earlier occupied by the leaving group. Let us understand with the help of this example. Say this is the leaving group, some reaction has occurred and the group that has occupied this position, it comes on this direction and all these three groups they have gone in this direction. That is, overall molecule has got inversion of configuration. We observe this thing, this type of inversion in mainly SN2 type of reactions. Then next is racemization. Racemization is that if in a reaction we start with a pure enantiomer and after the reaction we get mixture of both the enantiomers of the product, dextrorotatory as well as levorotatory, that is we are getting a racemate or racemic mixture. Say for in this example that this is a leaving group, in some of the molecule the incoming group has occupied the same position as it is leaving group and in some molecule has got inversion and group has got opposite position. If the two isomers are formed in 50-50 ratio, then the racemic mixture will be optically active, but sometimes in many reactions it is not the 100% racemization, one of the isomer may be more and other may be less, that depends upon the other factors in the reaction. But if both the isomers are formed, we call such a process as racemization, and generally this type of observation we find in SN1 type of reactions. Next we take up resolution. Resolution is the name given to a process which involves separation of racemic mixture into its components. There are different methods which are used for this process. One is the mechanical separation. This method is applicable for those mixtures only where the enantiomers form different crystals which themselves are enantiomorphous, and actually it was this type of separation which led to the discovery of stereochemistry. It was Louis Pasteur who separated the crystals of sodium ammonium tartrate using a tweezers and could get two different type of crystals which were mirror image of each other, and from there all this stereochemistry generated. The another method is crystallization. In this method, a crystal of one enantiomer is added to a supersaturated solution of the racemic mixture. Then what happens? The molecules of one particular enantiomer that we have added, that starts developing their crystals on those seed crystals which we have added, and other remains in the solution. Another method that is used is biochemical resolution. There are certain bacteria or fungus which consume one of the enantiomers only when they grow in the presence of racemic mixture. And what happens in the process? They consume one and another isomer can be recovered intact. The disadvantage of this method is that one of the isomer can be obtained and other is lost. Actually, this principle is based on the method that in most of the biochemical processes, even in our body, we use one of the isomer and other is useless, such as we use glucose in large amount as the source of our energy. It is only the D plus glucose that our body can digest or can consume. The other L isomer of glucose is just useless for our body. Our body will not be able to digest it or get energy from it. The another method for the separation of a racemic mixture is used, that is the most common method, is formation of diastereoisomeric salt. Diastereoisomeric compounds we have discussed earlier that they have different physical properties and it becomes easier to separate them. So, in this method what is done, that a given compound is converted into a diastereoisomeric salt which can be separated by fractional crystallization. Suppose we have an acid which is present as a racemic mixture. What we do, we add a base with one of the enantiomer, that is either dextro or levorotatory. This base will form the salt with this acid and we will get two salts. One will be plus acid plus base and another will be minus acid plus base. Now, these two salts are diastereoisomers and they have different solubilities, different crystallization, and they can be separated. Similarly, we can use this process for a mixture of base also. In that case, we will use one isomer acid, or this can be used for other type of compounds, like we can even form esters. Suppose I have mixture of this acid, I can use one pure enantiomer of an alcohol, let them react chemically, form the ester, and then later on the two different esters which are diastereoisomers can be separated and from them acid can be recovered by the process of hydrolysis. Then one final method that is used these days is by chromatographic separation, but this separation occur when we use a adsorbent which itself is optically active, and some of the common adsorbents which are used these days are lactose, quinine with silica gel, etc. So, these are the methods which are in use for separation of racemic mixture. Now, let us see what we have done today. In our today's session, first we will review what we did in our last session about the stereochemistry. We discussed that there is a need for the nomenclature of configuration. We discussed that two general methods are used. One of them gives a relative configuration which is difficult to remember. Another is absolute configuration. They are represented by R and S. We discussed some terms: retention, inversion, racemization, and then we discussed the methods which are used for separation of racemic mixture. Now, in our next session, we will talk about conformations. We discussed earlier that conformation are the different relative arrangements which are obtained by rotation across single bonds. So, we will be talking about this in our next session. Thank you.